There are many dark matters candidates through over the wide mass ranges, and the sub-electron volt mass Q, the dark matter show the wave behavior in the ultralight mass Q. This is called the wave dark matters. And typically the wave dark matter show the harmonic oscillation behavior. But today I want to talk about the other characteristic of the wave DM. First of all, there's wave interference, and the second one is the solitonic behavior by solving the Poisson-Schrodinger's equation. The wave dark matters can be described by the field configuration over the space-time, and one can define the energy density. And because the dark matter has some specific velocity dispersions around the galactic halo, this gives the momentum dispersion K. And the build configurations of the wave DM can decompose as the Fourier modes with the following plane waveform with the momentum and the frequency. And the energy density can be obtained by the scales of this build configuration. So the scales of the build gives the interference of the difference Fourier mode. So the second term corresponds to the cross term, which is represents the interference between the difference mode. And the typical momentum difference is given by the mass times the velocity dispersion. And the corresponding variation scale in the space is given by the Broglie wavelength, and also frequencies can be obtained by the dispersion relation, and also the characteristic time scales of this interference variation can be obtained. And if the n moves that contributes with the random pace, then the fluctuations of the field amplitudes are given by the root of the n by the statistical property. So the fluctuations delta size over the original amplitude is given by the order of the 1, and also for the energy density. So the interference of the wave dark matters in the halo naturally produce the order of the unity density fluctuations for the scale of the de Broglie wavelength and the corresponding time scale. This is called the granular structures with interference of the constructive and destructive ones, and this is consistent with the simulations of the wave dark matters. The second characteristics of the wave interference is the vortex structure. Let's start with the wave decompositions. The fluid velocity is determined by the phase term of the exponent. The gradient of the phase is related with the velocity vectors. And one can define the vortex structures, which is the line in the 3D where the field configurations vanishes by the destructive interference. This implies that the energy density also vanishes along this line. And in this point, the amplitudes are 0, so the phase are also the undefined over this line. Now consider the closed loop surrounding that line, and in this case, the over this closed loop, psi should have the continued pace due to the single valuedness. So the differences of the pace over this closed loop should be disguised by the integer. So if one integral is the velocity over this closed loop, then the velocity is related with the gradients of the pace. So this gives some number lattice with the integer. Here m is just a mass. So this gives the continuations of the circularized closed loop, which characterize this vortex structure. Near this vortex core, one can expand the barrel configuration. The burst terms are vanishes, but the next leading order terms are given by the gradients of the psi. This implies that around this vortex structure, the barrel configurations of the size are proportional to the radial part, so linearly increase, and also the energy density is given by the proportionality to the R scale. So by using that, one can obtain how the velocity terms grows about the radial part R, because the azimuthal angle, the pace status, winds around this vortex structure. So the fluid velocity is proportional to the 1 over the R. So this means that the densities are vanishes at the core, but the velocities are circulated 1 over the R, and the circulation of the loop is the context. This structure is called the vortex, as shown in this figure. So we talk about one phenomenology, the wave interferences of the ultralight dark matters. But now I want to talk about some solitonic core. This comes from the balance between the gravitational effects and the quantum projects in the Schordinger-Poisson system. The Schrödinger paths correspond to the quantum mechanics, and the Poisson paths correspond to the classical gravity. From the Euler equations for the momentum conservation, there is a quantum project term, the second term in the right hand side, and the first term corresponds to the gravitational potential. One can compare this term with the gravitational potential and the quantum project term. Then we can obtain the relation between the mass and the radius of the Solitonic core. So the core size is given by the functions of the core mass and the wave dark matter's mass. And there is a maximum bounds on the mass to avoid the black hole collapse. The Gm over the R should be less than the 1. Then using the relation between the mass and the radius, and one can obtain the maximum possible bounds of the Solitonic core. This is similar to the Chandrasekhar limits of the boson star. Also, one can consider that the self-interaction term of the ultralight scalar field. Then this term gives additional term in the Euler equation, and because it behaves like the plasmas, so depending on the sign of the Cortic coupling, this plays a role as the repulsive one or the attractive one. For example, the positive lambda, this gives the repulsive force. So the self-interaction provides the additional outward pressures. So if it dominates over the quantum projects, then the balance conditions changes with the comparison between the gravities and the self-interactions. Then the relation between the mass and the radius will be changes. And conversely, for the negative cortex, it behaves like the attractive interactions, so the sharp interactions enhance the gravity impact. Also the maximum stable masses changes. Now we talk about some density distributions in the wave dark matters. For the core dark matter case, this follows the density profile with NFW from the collision loss N-body simulation. Here the RS is some characteristic scale and the low S is a corresponding density. Its asymptotic behaviors is there some inverse power. So there is some central cups when the R goes to 0. This is a small cups problem. But for the case of slow-wave dark matters, it is shown that the Solitonic core profile as solutions of the Schordinger-Poisson equation. Now the density profile has some finite values in the R equal to the 0. There will be some core size given by the RC and the central density, the corresponding scales of the low C, and the asymptotic behavior it has some finite values for the small r, and in the barrel wise the r to the minus 16. So the wave dark matter profile has a flat core and a much steeper outside compared to the core dark matter density profile. In realistic cosmological simulation, the halos are given by the combined halos, combined density profiles for the wave dark matters. In the small r, this is given by the Solitonic core, but the large r, it follows NFW-like envelope. So such a wave dark matters was originally motivated by the small-scale tensions of the core dark matters, especially the coarse core problem. In the core dark matters only simulations, the inner density profile follows the inverse power, so this makes the infinite values in the central curves. But the observations of the dwarf galaxy prefers a nearly constant density in the inner profile. This means that the cores rather than the curves. So the wave dark matters model can naturally produce the Solitonic core due to the content projects with the inner behaviors. And also the wave dark matters can address the kiloparsec scale cores in the dwarf galaxy. When the wave dark matters mass is around the 10⁻22 electron volts. This mass can yield the core radius with observes the dwarf galaxy rotation curves. The core radius of the Solitonic scales are given by the functions of the halo mass and the wave DM mass. And both the 10⁻22 electron volts of the dark matter mass, the core radius is around the kiloparsec, which is the constant with observed values of the dwarf galaxy. However, such ultralight masses are surpluses on the structure formations of the small scale for the some specific power spectrum. This modifies the Lyman-Apopolis status, so the observations of the Lyman-Apopolis constrains the such a mass scale 10⁻21 to the 10⁻20, so that this makes additional tension because the dwarfed core requires that the 10⁻20 electron volt. But the cosmological power spectrums argue that the dark matter has low bound mass around 10⁻21. So the current status of wave dark matters are still not excluded, but the original motivations of the small-scale structure problems are significantly constrained now. So now the modern CDM simulations that includes baryonic feedbacks. So the combinations of the baryons and the CDM can generate the core-like inner density profile. So the CDMs is not clearly ruled by the galaxy data. So the still core dark matter simulations is alive. So summary, today we talk about some phenomenology of the wave dark matters, but with the wave characteristic of the ultralight mass scale by considering the interference. There is a superposition of the many variables, and this gives a closed term, and by the construction of destructive interference, some real configurations will vanish. And the destructive interference can create the vanishing fields along the sum line, and this can give the vortex structures, which is quantized by the loop. And also by solving the Schordinger-Poisson equations, the wave dark matters can give the Solitonic course by the balance between the gravitations and the quantum pressures. And in this case, the central region shows that the constant density profile, which can resolve the Korolkov's problem in the CDM model. But also the wave dark matters can resolve the dwarf galaxies associated with the consistent values of the radius, but the Lyman probability status excludes the such ultra-Lyman scale.